In problem number 1, we are trying to determine what flow rate a pump would have to deliver to supply 1 inch of water to a lawn in a period of 6 hours if the lawn has a surface area of 1.25 acres. And we're to determine this flow rate in units of gallons per minute. Well, the first thing we want to do is get a little better picture of what this would look like. And so really what we're looking for is what is the volume of 1 inch of water that covers an area of 1.25 acres. The first thing we need to do is determine in units that we're comfortable with what an acre is. Looking in the internet, we find that 1 acre is 10 square chains, and 1 chain is equal to 66 feet. Using that, we'll take the area, convert that into feet, and take the thickness and convert that into feet, and then take the volume in cubic feet and convert it into gallons. So we take our volume, which will be 1.25 acres, and multiply that by 10 square chains per acre, and there is 66 square feet squared per square chain. The thickness is 1 inch, and we'll divide that by 12 inches per foot, and also noting that there's 7.4805 gallons per cubic feet, and we determine that this lawn would require 33,943 gallons of water in order to cover it 1 inch thick. Our flow rate would be this volume over a period of 6 hours, and then convert the hours into minutes, and we find that the flow rate is 94.3 gallons per minute. So if we had a pump that could deliver up to 100 gallons per minute, that would be satisfactory for this problem. Problem 2 asks us to calculate the weight of the lunar rover used in the Apollo 15 mission, which has a mass of 210 kilograms. And we're to report the weight in both units of newtons and pound force. When we calculate the weight, we need the acceleration of gravity, and on the moon it's significantly different than that on Earth, so we need to find out what is the gravitational constant for the moon. And little research will tell us that its acceleration of gravity is 1.622 meters per second squared. Using the weight is the mass times the acceleration of gravity, we can calculate using 210 kilograms, multiplying it by the acceleration of gravity, 1.622 meters per second squared, and then converting that into units of newtons, where 1 newton is equal to 1 kilogram meter per second squared. And we'll find that the weight of this lunar rover is 340.6 newtons. We can then calculate what this would be in pounds force using the conversion factor that there is 0.22481 pound force for every newton, therefore giving us a weight of 76.6 pounds force. On Earth, this lunar rover would have a mass of over 460 pound force, whereas on the moon it's with less than 80 pounds force, which is a weight that an adult male would be able to carry quite easily on the moon. This problem is a manometer problem where we have 2 pipes joined by a horizontal pipe. Initially, both pipes are filled with water, and the height of each pipe is 5 meters with a diameter of 2 centimeters. We're going to add an iron disc to the pipe on the right, and this disc also has a diameter of 2 centimeters. This disc can then slide down the pipe on the right and force the water out on the pipe on the left. There was an error in the original homework problem where it was said right, but the iron disc will push the water out of the pipe on the left. And we're trying to find the thickness in which the disc would be so that the disc stops at the 2.5 meter mark on the pipe. Knowing the properties of the manometer, we know that the pressure within a continuous fluid on both legs of a manometer is the same at the same horizontal elevation. Therefore, if we drew a line immediately under the iron disc on the right, that pressure would be the same as the pressure on the left-hand side of the manometer, which we'll call P1, and P2 equal to the pressure on the right-hand side. P1 is just the atmospheric pressure plus the pressure exerted by the fluid, in this case being water, which will have a density of rho sub water times the gravitational constant g times the height of the fluid above the level that we're looking at. And that will equal the pressure on the right-hand side, which is the pressure of atmospheric pressure, plus the pressure exerted by the iron disc, which is equal to the density of the iron times G times the thickness. In this problem, we're calling it T. Those two pressures are equal to each other, and therefore we can rearrange the equations, noting that the atmospheric pressure subtracts off on both sides of the equation, and that the thickness would be equal to the density of water times the height of water divided by the density of the iron. We'll also note that the ratio of the two densities is also the same as the ratio of the two specific gravities. So our equation would have the specific gravity of water, which is 1, divided by that of iron, which is 7.7, times the height of the fluid above the line in the diagram, which is 2.5 meters. Therefore, the disk would have a thickness of 0.325 meters, which is 32.5 centimeters, or 12.8 inches. In problem 4, we're to determine how many kilograms of carbon dioxide gas we exhale in a given year, noting that each breath contains approximately 1.2 liters of air, and this air contains 5% carbon dioxide on a volume basis. The first thing we need to do is estimate how much we breathe in any given period of time. And let's pretend or assume that we take 15 breaths in a minute, and we know that each breath contains 1.2 liters of air, and 1 mole of air occupies a volume of 25 liters. Now, if we have an ideal gas, which air usually is at normal temperatures and pressures, a 5% on a volume basis for carbon dioxide is the same as 5% on a mole basis. So this air we breathe out contains 0.05 moles of carbon dioxide for every mole of air. And the molecular weight of carbon dioxide is 44 grams per mole. In this calculation, we'll find that we breathe out 1.584 grams of carbon dioxide every minute. Extending this clear to a year, taking that flow rate of 1.584 grams per minute, and noting that there's 1,440 minutes in a day and 365 days in the year, and then converting into kilograms, we will find that the amount of carbon dioxide we exhale in a given year is approximately 832.5 kilograms.